So, welcome to the third lecture of aspects of algebraic number theory. Today we're going to talk about Mordell's theorem and its proof. And the proof of Mordell's theorem basically consists of 4 lemmas, and I think today we're going to cover the first 2 lemmas. Next week we're going to cover lemma 3 and maybe a bit of lemma 4, but probably we will just skip that part. So this is basically a new topic because we are going to talk about heights. So what's the height and what is it for? If we look at different numbers, then a human being would say, okay, so this and this and this number, they're basically the same. This is pretty far away from this one, and maybe we also take this. This is close to this number, but far away from this number. But if you're a computer, you think about numbers in a totally different way, because you think about how much space do you need to store them. And then this number is very complicated because it needs a lot of space. This basically needs as much space as this one, or this one, or this one, or this one. So the height will be something that helps us measure how complicated it is for a computer to memorize a number. And how do we do this? We will talk about different heights, and it will usually be clear from the context about which heights we're talking about, because now we're talking about heights of rational numbers. Later we will talk about heights of points on elliptic curves, and maybe at some point we will also talk, not today, not next week, we will also talk about heights of elements of number fields, maybe. Define the height of a rational number. Okay, so we take the maximum of the absolute value of the numerator and the denominator. Is this well defined? Well, as we write it here, it's not well defined, but now it's well defined. So we take a rational number, we write it as m over n, where m and n are coprime, and then this is well defined. We have the maximum of the absolute values. Well, if you define a rational number where n is positive, you can also just get rid of those absolute values. I think usually people write it with just n here, because n is usually positive. Okay. Sometimes we like to play around with plus instead of times, so we also define this. It's just a notation. So what properties does our height have? If we take a set of points where the height of all the points is bounded, then this set is finite. This is basically the most important and most crucial property of the height. If we have this, or let's yeah. Or any bound here, this will always be finite because we only have finitely many possibilities for the numerator and the denominator. It can be between -5 and 5. So we only have finitely many rational numbers, and sets of this kind are always finite. This is what you always have to keep in mind, because whenever you do something with heights, you usually always have to use that you have this finiteness property. This also, of course, holds if you replace it by the small h instead of the capital H, because we then only have log 5 as well, e to the bound as a new bound, but the finiteness property stays always the same. So now we want to also have the definition of a height of a point on a curve. So here we make it very easy. We just define the height as the height of the x-coordinate. Of the point. And analogous in analogy, we can also use the small h. Okay. So if we look here, what happens if we want to compute the height of 1 or the this height of 1? This is just 1. And this is just 0. And we kind of want to do the same here. We just define the height of the point at infinity. We define it as 1. And this, we define it as 0. This will be our main tool in the proof of the theorem that I will now tell you about. Now, maybe we want to compute some examples, but well, this is so easy. Let's look at our numbers there. For example, the height of 10. 10 is 10 over 1. So the height of this is 10. The height of 3, 4, 5, 6 is 10 to the 6. So this is, the number is basically 1, but the height is very large because it's just a complicated number. Height of 1 is 1. Height of 0 is also 1. And let's take also the height of 1 over 10 is also 10. So you see, it's just it has a very close to connection to what number of bits do we need to store such a number. Okay. What's now the theorem that we want to prove? Our proof is Mordell's. Our goal is Mordell's theorem. which is just that the group of rational points on elliptic curves is finitely generated for any elliptic curve. A generalization of that is the theorem of Mordell-Weil, which we will not prove. It's just where we, instead of the rational numbers, we take a number field, and then the statement is that the points on the elliptic curve with coordinates in the number field is still finitely generated. But this, we can remember that this is true, keep in mind that this is true, but this is what we want to prove. Okay. For this, we need 4 lemmas. I will state the 4 lemmas, then I will prove Mordell's theorem, assuming that we already proved the lemmas, and then I will start proving the lemmas step by step. Lemma 1. Okay, lemma 1 is for every real number m, the set of the points of EQ with bounded height by m is finite. Well, we basically can prove this right now, because we said that the set of bounded height in the rational numbers is finite, because we can only find finitely many rational numbers where m and m over n is in lowest terms, such that the height of m over n is less than a fixed bound. And since this is just the height of the x-coordinate, we get finitely many possibilities for the x-coordinate, and hence also finitely many possibilities for the y-coordinate, because for every x-coordinate we get at most 2 possibilities for y. So this basically, we proved it. The other lemmas will be a bit harder. So the next lemma says we fix one point on the elliptic curve, and then there is a constant that depends on the point that we fix and on the curve, such that we can bound how the height of a point, of any point, grows when we add p0 to that point. So this p is arbitrary, but p0 is fixed, and k0 only depends on p0 and e, but not on the p that we then are free to choose.
Sorry,
Yeah? Yeah, but when yeah, maybe it's good like this. We don't need it. Yeah, or maybe I can. And this is also not good. Okay. Is it okay like this? Okay. Then I will continue here. Next lemma is about the height of the double of a point, because we want to double points. So this means well, k only depends on the curve, and if we double the point, the height grows quite a bit, but this is explicit given by 4, and this is only depending on the curve. Last lemma. Is that the index of E of q over 2E of q is finite. And this is just the number of elements in this group. This could almost be something that we do in AGLA, because we also do equivalent relations there at the moment. Yeah, but they would get crazy if I told them what an elliptic curve is. Okay, so these lemmas, this is all that we need to prove Mordell's theorem. And basically, what you also can do is look at abelian groups that have a height defined on them that fulfills all those properties, and then you also have that it's finitely generated. So there are abelian groups that have nothing to do with elliptic curves, but they have some height function that fulfills those properties, and then we also have the result that those are finitely generated, because what I will do now basically only depends on the fact that we can add on our group, and that we have this height with this with these properties, and the proof doesn't depend on the fact that's an elliptic curve. Okay, so now we assume that we have all those lemmas, and we prove the Mordell theorem. Okay, so we said that the index EQ over 2EQ is finite. So we can just choose a system of representatives in this group. It's finite. and we call them Q1, Q2, until Qn. So if we now take any point on our elliptic curve, we always find some Qi in here, such that P plus this Qi is in here. We call this I1. Okay, we want to write it with a minus, but it doesn't make a difference. Okay, so what does that mean? It means that P minus Qi1 is of the form 2 times a point on the elliptic curve. We call this 1, probably. And so this P1 is just a point on the elliptic curve, but with this point we can do just the same like what we did with this P before. So we can find some I2 between 1 and n, such that P1 minus Qi2 is in 2eq, so that it's of the form 2 times a point on the elliptic curve. This gives us P1 minus Qi2 is the double of a new point. And we continue like this again and again, and again and again. And again and again and again. And the question is now, when do we stop? Let's think about it later. At some point we stop. We will still figure out when this point will be reached. Let's just write down what this means for our P1, P. So P is 2 P1 plus Qi1, and P1 is 2 P2 minus Qi2, plus. And P2 is 2 P3 plus QI3 and so on. And in the end, we get 2 to the m sorry, this is the QI. But here the index is different, so this is let's just do it like this. I think this should be correct, but the basic idea is clear. The important thing is that in the end we have written P as 2 to the m times some point plus something in the double points, so in 2eq. This are all double points. Okay, so so now the question is, until when do we have to do this procedure, and what does it mean then? Well, we can just think of any bound that we like and say we want to do this procedure until the height of this Pm is smaller than 10, for example. Then we see that P. Oh, and we. Let me go back one step, because I have this here in another order.
Sorry, I have a question.
Yeah.
Why is with QI1 added the sum still in 2e?
Because here. Because we have that E of Q over 2EQ has a finite set of representatives. So just like if you consider Z mod 10Z, you can take any point in here, and then you can find a representative in the equivalence classes here, such that you make it go in here. Well, let me try to explain that better. Or did that already answer your question? Not really, right? Okay, let me go away from the examples. So we take just any point on the curve, and we know that that if we divide out all the multiples of 2, then this is only a finite set of representatives. So all the points that we take on the curve E of Q and kind of project them into this group here, they have to land in a finite in one thing out of a finite set of representatives. This is, if you compare it to this one, is basically like if you take some integer and want to project it in here, then you can find a number in here that you, no. Maybe I should not explain it with that example. Yeah, let's forget about this example. This doesn't help. Let's go back to the actual explanation. So you have a generic point on the elliptic curve, and you want to do something to it to have it of the form 2e of q. And since there are only finitely many possibilities of being kind of in the reduced form, modulo 2eq, you can find one of those equivalence classes, take a point in there, and then this will get rid of the not even part. Well, yeah, let me say not even part. That's not the double of a point, because this is basically what those points represent. They represent the finitely many possibilities of being away from not being the double of a point. Yeah, maybe you have a better explanation.
I think there's maybe just a tiny mistake there, because qi1 is not in 2eq. And if this parenthesis part was in 2eq, then this whole sum would also be, because the first point is also double of something, and that would mean that p is double.
Oh yes, oh yes, oh yeah, maybe this is the problem. Yeah, this is not in 2eq, but in the finite set of representatives of the group E mod 2eq. Yeah. Yeah. Sorry, yeah, that was wrong. Yeah. Okay, good. Oh my God. Yeah. Okay, so let's try to get back on track. Yeah. Yeah, I just should not try to explain things with examples. This doesn't work very well here. Okay, so what did we do? Now we found a way of writing some arbitrary point as something plus something that's a linear combination of finitely many points. Now we have two questions open. And one question is, how long do we want to do this procedure? And what can we then say about this PM? And the goal is that we first want to show that the height of this PM gets smaller. We will use one lemma for that. And then we will say if the height of the PI that is here gets smaller and smaller each time, then these will also just come from a finite set, because then this PM will be of a set of points of bounded height, so it will be finite. So we can then say that P will always be a linear combination of something out of a finite set because of the finiteness property of the height, plus something from a finite set because the lemma 4 says that this is finite. So let's see what we can say about the height of this PM. So just consider the series of this P1 until PM. And we just want to calculate the height. And we just look at this. So for example, pi is pi minus 1 minus qi I. Oh, I should not index I with I. Let's take this. Okay, so the height of Pn minus 1 minus Qin is the height of Pn. Okay, and we can use lemma 2 that tells us the height of 2 points, Pn minus 1 plus Qin. Uh, 2n minus 1 plus k0, where k0 depends only on p0 and e. So k0 depends on this Qin and on e. So and on e. So let's maybe take here k0 comma Qin. And here we have this inequality for every step here. And of course for the first one where it is p plus Qi1 I1. Are the indices correct now? I hope so. No, it's here n minus 1, and so this is, I think now it should be correct. Okay. Sorry. Okay. So now with this we can relate the height here and here. And if you look at what Pn minus 1 plus, the index was correct because this is what we have from the lemma, sorry. Oh yeah. Yeah. Exactly. Yeah, and here the indices are correct. Okay. So this is what we have from these equations, and this is what we have from lemma 2. So it tells us that, so this gives us a possibility to relate the height of Pn and Pn minus 1. Namely, we have then this. Is this just by construction, and by the lemma we have this In. Okay, so we can go through everything and get that the height of Pm is something like 2 to the m times the height of P plus some k nu. K nu will be something like k0 qi1 plus 2 k0 qi2 plus 2 to the 2 and so on, but it doesn't matter at all what k nu is. It's just important that k nu only depends on all those qin and on the curve. So it doesn't depend on what p we choose in the beginning. So, but this says that from the point where we start choosing a p, we can bound pm, and we oh wait, do I have the? Did I miss a minus? One moment. Ah, yeah, no, yeah. So let's take one more step until I conclude something. So we have used lemma 1 and lemma 2 and lemma 4, but we have not used lemma 3. So let's see what we can do here. We have something that relates the height of PM with something that's only dependent on something that we choose in the beginning and the height of P. And we have that P is something like 2 to the m times PM plus something else, which is from a finite set. So how can we relate the height of P and the height of 2 to the m PM? For this, we want to bound this. Okay, it says what happens when we double a point. It tells us that this is at least 4 times the height of P minus K, where K only depends on the curve and it doesn't depend on our point. So here we have 2 to the m times P, so we will use this several times. And oh, wait one moment. No, let's look at this at one step in the middle to find out what when we need to break. So we have here this Pj. We take it just out of one step here, where we have Pj minus Qij plus 1 is equal to 2 Pj plus 1. Because this is exactly what we want. This is shown. This is already in the form 2 times a point, which is exactly what we want to use here. So 2 times Pj is Pj minus 1 plus Qij. I hope I get the indices correct. No, it's minus. And this sorry, I have to not get confused with the indices. This is correct, right? Yeah, I think so. Okay, Good. But now we want to use lemma 2 again to get the height of the 2 points. And this is at most the height of pj minus 1 plus the height of qij. No, sorry. Plus k0, where the k0 only depends on the second point, and the second point here is our qi. So we have something that depends on the qi, and of course always on e. Okay. So what does this tell us? This tells us that the point, the height of the points in our series here, this pj, gets smaller all the time, and we only have to find out what is the how can we explicitly use this to find out when at which point m we have to stop and what we can conclude from this. Let me write that down. Sorry. I called them let's just take a totally new K. Sorry. Okay. The height of this point pj we divide this equation by 4, and let's take a break now, and I will find my thoughts again after the break. And let's have a break until 11:10. And then continue afterwards.